Hello, my name is Harry Wilcox and today we're going to be reviewing the Novacam tube inspect system. So behind me we've got the system. Effectively how the system works is we've got a Z axis, an X axis and then a rotary axis. So to demonstrate those, our X axis is moving in this orientation, we've got our Z axis moving up and down throughout the component, and then we've got our rotary axis, which is this chuck at the bottom. So the principles of how the system works is the technology that's used is laser interferometry. So if you were to zoom in onto my hand, you can see that there's a spot size. So as we take a measurement, what happens is the probe will drop down into the component. We rotate the component at the same time and we build a 3D geometry of the surface. So from that we can look at cylindricity, roundness, diameter measurements, radiuses, thread measurements and also roughness within certain parameters. So as a very top level overview of the tube inspect system, it gives an insight as to what it's used for and the types of features we can measure. So now we're going to take a look at actually creating a measurement routine to be able to measure the internal thread or thread features of this component in my hand. So what I'm going to do is place this component into the machine and just check that the run out of the component in the chuck is okay, which it is. With some more complex features we might have to create a specific fixture to hold the component to make sure that we're running as true as we can to that axis. So the idea behind how we program on the system is we use this joystick. So we've got our Z movement, so I can move up and down, as well as moving in the X and Y, in the X positive and negative, sorry. So if I drag down into the center of the component, so this is just the movement of the system. So I'm now inside the bore. So what we're going to do in our software now is we're going to go to what's called the A scan. So A scan is effectively the intensity of our interferometer. So as I was to come down into the component, you can see the signal spike. So the signal spike that we have here is quite small, but as we rotate it around, we can see that the spike is moving, which is effectively the major and minor pitch of our thread. So what I'm going to do is just bring the interferometer slightly close to the part, and now you can see we've got the peak or the signal in the preferred position between our blue lines. Now we can move the position of those blue lines depending on the fit or the diameter that we're trying to measure. This sensor here we're trying to work with at about 5 millimeters, but we do have some sensors that can view up to about 230 millimeters. So depending on the specifics of the application that you might have will depend on the different types of setups. We've got some setups where the Z range is about 2 meters, also with an X range of about half a meter. So there's lots of different types of systems. When you're talking about Novacam, you're talking more about a technology as opposed to a specific off-the-shelf product. Okay, so now I've got the sensor in the correct position. What I'm going to do is I'm going to click the back button on our joystick here. I'm now going to drive internally in the component to my finished position, and I'm going to click this button again. And then on the top of the controller, there's a number 2 button, and what that does is it inputs me a scan definition into our code. So within this setup now, I can define how I would like the program to run. So what I'm going to do is go on to mode, and I'm going to right click and I'm going to run a spiral scan and click OK. Now I'm going to go to options, and this is our processing options. So how or what is it we're trying to measure? So if I go to cylinder, I'm just going to fit this to itself. So I'm going to say cylindricity only. So now if I roll across, the other key one to look at is our Z step. So this is effectively, I'm going to drop 0.12 millimeters for every 360 degrees of rotation. So as an initial scan, what I'm going to do is I'm just going to set this to 0.25. So for every 360 rotation, we're going to travel down 0.25 a millimeter. And now what I'm going to do is click start. So that has effectively created me the scan definition, so a program to measure a sample. So now effectively that's going to go and run. So as you would have seen in the mode, there's lots of different types of scans that we can create. So if we were using a roughness measurement for an example, we wouldn't use a spiral scan. We'd be looking to do a profile scan, sort of up the internal in the Z axis. And then what we can do is we can iterate with our rotary stage. So we could take maybe 5 line profile scans on the internal of a component to be able to depict the different roughnesses or look at length positions. So if we needed to do the pitch length of a thread, we would use profile lines and conjunct that with or merge that with other types of scans to get other types of features. So for length measurements, the profile scans are the best to use, and doing diameter runouts, the spiral or the circle scans can be used to do that as well. So as you can see, we've got a scan completion. So in this top left corner here, what it's doing is it's telling me how far into the scan we are. So I'm currently running at that 0.25 Z step. So we're going to get a relatively coarse data set. Now we've got some examples where we would run this at a 0.1 step, so you'll see a lot more data on that internal surface. So when it completes, the probe drives out of the internal bore, and what we'll see now is a point cloud data set from our scan. So this goes straight into, in this sense, Polyworks, whereas we can process the data in lots of other softwares. Effectively, we're using this system to obtain a high accuracy point cloud. So what we do with that, we're relatively flexible with. So you can see here now, so we've got the data for the thread. So if we were to zoom in, you can see all of these individual points that are taken, and you can start to see the form of the thread. Obviously our pitch that we've used is slightly too big. So what we would do is we go back into our software and we would refine that down so that we're getting more information on that thread. Okay, I've got an example preloaded of the other end of this component with a much more dense scan. So you can see as we zoom in, we're picking up all of that detail. There's a few little surface defects here that you can see. And what we can do is we can quantify the size, shape and position of those from our scanned definition. Okay, so that's a very quick overview as to how we can use the system to scan, how we would create a routine or a program, and effectively the only last step that we would have to do is to either measure the sample in Polyworks or create a macro set to be able to do that automatically, depending on your sort of part volumes and variation. So now we're going to look at an example of doing a profile scan. So in this sense, what we're going to do is go back to our joystick. We're going to set ourselves a Z0 or a start position. We're going to drive down into the component and click the button on the back of the controller again, and then click our number 2. So what that's done is it's telling me that within those positions or those Z set heights, I'd like to take a scan. So now on our mode, what we're going to do is we're going to look at Z and R area scan. So this is the scan definition that we use for profiles. We're now going to go to our options, and I'm just going to again measure this as a cylinder. So if I roll across now, we've got our Z step. So this now in this type of scan is effectively defining the speed in which our Z scan is going to run. So what we're going to do is I'm going to set that to be around 2.5 millimeters per second. Our R min and our R max are effectively, now we're not rotating the component, we're going to set the first one to be 0, and we're going to set the second one to be 360. So what I'm doing is I'm telling the system that within these boundaries or these areas, I would like to measure within a sort of full circumference of the feature. Our R step, what I'll do is I'll set this to be 90 degrees. So this is going to effectively take a profile every quarter. And now if I click start, you'll see that what the system's going to do, as opposed to coming down and measuring a spiral, what we're going to do is we're going to look at a profile measurement traveling at 2.5 millimeters a second. So we can vary the speed depending on what it is you're trying to do. Obviously on a thread, the slope angle is relatively difficult to obtain optically. So the slower we go, the more detail we're going to get within those profiles to be able to look at things like the flank angles, pitch lengths, that kind of thing. So as we're scanning through here, obviously the component's rotating. So the scan is completed. So again, this is all optical on this internal feature. So what's going to happen now is we're going to load up our latest point cloud. And you can see that if we zoom into some of these areas, where we've traveled down low enough, we've started to pick some of the angled features on the internal here. So what we can do is from here, we could say I'd like to measure a feature. So this would be your manual measurement to do this. There's a lot of chatter on this internal feature, which is good to see. I can create a line through this axis, a line on this slope, and what we can do is measure that internal chamfer. If we were looking at the thread, we could do the same thing. So if I wanted the flank angles, I could take a point here and a point here, a point here and a point here, and then do the same principle again to measure that angle here. Okay. So this is the manual sort of process of how you would measure features. What we'd be looking to do for sort of productionized systems is to have that all automated, so we're finding features automatically within Polyworks and creating you that measurement report or that measurement output that you need effectively within a click of a button, which would be your start button on the Novacam system. Okay, so it's a very quick overview, but what we're trying to do is show you the different types of measurement methods that we've got on the system. So now we're going to look at outputting a roughness value. So what we're going to do is we're going to take a profile measurement on the internal of a component. We're actually going to swap the component over. So I've got a through diameter here. So it's a continuous diameter through the center. So what I'm going to do is just take our threaded feature out and just place our other component into the chuck. Okay, so we've got that placed in. So what I'm going to do is take my controller again and I'm going to drive into the center of the component and just make sure that I refine my signal, because obviously on a roughness measurement we're looking at single digit microns and quite often sometimes lower than a micron. So we just need to make sure that our signal is really crisp and we've got a really good sort of sine wave or bell curve, I should say. So when we go to our A scan now, you can see that we've got a signal. What I'm going to do is just refine the position of my blue boundaries so that as I rotate, that this signal is very close to those blue boundaries. Effectively what this is showing is on the bottom level where our 0K is, if I show you with the mouse, this is effectively our ambient noise. So you can see that constantly the sensor is finding data and what we've got here is our initial contact with the surface. So what we're doing is as we rotate round, you can see that the signal's changing. Obviously any run out within the component and also the chuck could be shown here. This is component run out. So we're seeing the movement of that signal. So I'm just going to drag this across to here and open this one up slightly. So from here I know my signal's okay. So we're going to set a start position. So I'm going to use my joystick again, click the back button, drive down inside the component and click the back button again and input that code into the software. So from here, what I'm going to do is select our Z and our area scan, which is our profile measurement, as we touched on before. Now on my processing options, what we can do is go to roughness, and I can click OK, OK. What that's effectively doing is it's setting our cutoff length, so we can change that within our parameters related to the roughness. So we can select the different parameters that we use, the cutoff lengths. So within here, we can, if you've got specific requirements, we can filter that, add in the other export settings that you may need. So from here now I can go across my Z step. So this is our speed in a profile measurement. So what I'm going to do is drop this down to 2.5 millimeters again. So same as we had before, 2.44 is okay for what we're doing. We're now going to set our actual position. So currently rotationally it's at minus 1091. So we're going to rotate 3 times before we start our scan. So I'm just going to set that to be the actual position. And you'll see now that's mapped that to where the rotary stage is at the minute. So we're not going to rotate that set. I'm going to do the same again for our finish, our max. And the last one being, I need to change our R step. So this is the step between the two. So I'm just going to set that to 0001. And from there I can click start. And now what this is going to do is it's going to go into the internal. We're going to measure the roughness on that diameter. And what it's going to do is spit us out a number at the end with an RA and an RQ value. So as this is running, I'll run you through the principle of what the software is doing. So if I move this box here, now that the scan is completed, you can see we've got the data before we filter. We apply a median filter to that data set. We now look at sectioning with our cutoffs, so that we now export the waviness. We remove the waviness from our roughness plot. And effectively at this point now, we've got the margin removed and we've got our roughness value. And you can see the roughness of the internal of this component, we've got a 3.05 micron roughness with an RQ value of 3.76. So I can click OK to this now. And what that will do is it will populate me with a Polyworks profile if there was any other measurements that I was trying to do from here. So you can see we've got the roughness plot, which is effectively the internal of that component. Okay, so these are the individual points that are used to construct that roughness. So that was a very quick overview of how we can program and also measure the roughness using the Novacam system. So if you've got any queries, don't hesitate to get in touch. So thanks ever so much for spending the time to look over the Novacam system with me. Please make sure that you take away the principles that we can use the Novacam system for. So we can look at things like diameters, form, straightness, those internal geometries that people struggle with, angles, chamfers, radiuses, undercuts, all of those kind of features we can use the Novacam for. The last thing to take away, I know I touched on it previously, but the system we have here is a sort of demonstrator system. So we've got a set Z or a fixed Z movement of about 130 millimeters with a max diameter size of about 80. Now, using this technology, we're not limited to that size. So this isn't the only size of system you can purchase in the Novacam setup. We can go as big as 2.5 meters and sometimes longer, depending on the application. And also we can go wider on the diameters. So Novacam also supply a system called a tube inspect, which is we have here, and we've also got the bore inspect. So the bore inspect, or the principle of how the bore inspect works, is that the probe will rotate as opposed to the component. So in the example we have here, where I rotate the chuck, the component is moving. Now sometimes you might have a 60, 70, 150 kilogram component. We don't want to be spinning that on a chuck. It gets very expensive when you start to try and load components that heavy. So what we want to do is we want to bring the probe in on an axis, and we can rotate to the end of the probe. So don't be put off by potentially seeing very small components. If you've got larger components, we can still look to create your measurements on those samples, okay? So it's a very quick overview of the Novacam system. If you've got any queries, please don't hesitate to get in touch, and thanks for watching.